Hi everyone, my name is Cuthbert and I'm a PhD candidate in the Department of Geoscience and Petroleum, and today I'm going to present to you applications of data-driven models in reservoir management. So first of all, let us go through what is the motivations for this research. So the motivations, before we talk about the motivations, we need to know what is reservoir management means. So in general, reservoir management is the utilizations of available resources for us to maximize the recovery of the hydrocarbon productions from a reservoir itself. And over the decades, numerical reservoir simulations has been used as one of the tools to model a fluid flow in porous media and to help us to make decisions in reservoir management. And one of the use of it is to forecast the hydrocarbon production as shown. However, there's one main challenge about the use of NRS, which is actually the expensive computational footprints. And this expensive computational footprints happens when the geological properties of the reservoir itself is sophisticated, or we need to consider a lot of variables when we come to production optimizations. So one of the criteria to solve these solutions is we need to achieve a good level of accuracies, and at the same time we also need to achieve what Kenneth has presented, the need for speed. So one of the solutions to tackle this problem is data-driven modeling or data-driven reservoir modeling. As we know, the main ingredients for data-driven modeling is the data itself. And the data can come from the simulation itself or also from the real field. And in this case, I'm focusing more on the use of the data from the simulations itself. And the ideas is to actually establish the relationships or the mathematical relationships between the inputs and the outputs. And there are several state-of-the-art approaches as shown here. So some of them include the response surface models and also the reduced order models, as you can see. However, the limitations here include some of the simplifications or assumptions in the approaches used. And also, the state-of-the-art approach also shows some difficulty in capturing a non-linearity. Therefore, there's an alternative approaches used here, which is the machine learning, as you have seen from the previous presentations. And there are some examples shown here. Artificial neural network. And it will be the main focus used in this work. As you can see, artificial neural network is basically the mathematizations of the mimicking of the brain network itself. So how machine learning or artificial neural network can be used to build the proxy models? So before we go into that, we need to understand that actually proxy modeling is an objective directed task. That means before we build a proxy models, we need to know what the model is used for. So for example, if we go for dinner tonight, we want to cook some pasta, we need to know to buy spaghetti and stuff like that. So it's the same logic for proxy modeling. So as you can see in the pipeline here, so some of the general workflow, first we need to decide what input and output we need for the proxy modeling. And after that, since in this case we are using the reservoir simulation data, so we need to apply some sampling techniques to sample the data that we want and to create a database for training. And then we will partition the data into training, validation, and testing, like what Kenneth also has briefly mentioned just now. But the only difference is that some people might think that testing is actually to test the robustness or the predictability of the models itself. And it is actually unseen data. But in this case, testing data will be also within our database, but it is actually not used to train and also validate the models itself. But in this case, to further validate or to further verify the predictability of the models, we are creating some blind validation in this case. So blind validation is also another database that we use to actually check if the model is working okay. So there are some case studies presented here. So the general introduction is that we are using neural network to act as the proxy for the simulations models. Then after that, we couple it with one of the algorithms. In this case, we are using the particle swap optimizations to optimize the water flooding cases. And the aims is to reduce the computational footprints while, of course, achieving a good level of accuracies. So several questions to be addressed before we go into the case study is, which reservoir model to be used in this case, and what is actually the optimization problems that we want to solve in terms of reservoir management, and also how the training database can be generated or obtained, and how are we going to formulate our neural network, etc. So the very first step is to actually formulate the problems. As you can see here, we are actually trying to optimizing the NPV under water flooding cases. And the model that we are using is the benchmark ACT models. And as you can see, we need to identify the decision variable in this. So in this case, we are actually adjusting the fuel injection rates while maximizing the NPV. So based on this NPV, we need a fuel oil rate and also fuel water rate and also fuel injections rate. But in this case, we know the fuel injection rate. So the proxy that we built need to produce the output for oil rate and also water rate. So next, this is the model that we use, as I have mentioned. So we need to sort of formulate the models that we want to build for our proxies. So in this case, we have included the time steps and also the average permeability for every layer, and also the mean average permeability for every layer, and also the standard deviations for every layer, and the mean permeability for the perforated grid block for the injectors and also for producers. And also the U is the control of the injection rate that we use. And this one is the output that we are going, the output at the previous time step that we are going to use. So in this case, we are actually building sort of the dynamic models, so which is quite different with the previous presentations because we are actually building the models that can predict the output at every time steps. And in this case, we are actually building the two proxy models. One is the liquid production rate, and also another is the fuel water cut. So using these two output, we can actually calculate the oil production rate and also water production rate. The reason why we do so is that after our investigations, this worked best for our case. So having known what we need to build, so we implement the sampling techniques. In this case, we are using the Latin hypercube samplings. So we generate 60 injection scenarios, so 60 different combinations of controls, and then we generate the data that we want. And we also generate some additional scenarios for blind validations that I mentioned just now. So after that, we will do some data preparations by normalizing the database that we have. And then we perform the data-driven modeling to train the models. And in this case, we are using two different machine learning techniques. One is a feed-forward neural network, and another one is a long short-term memory. And then we couple it with the optimization algorithms to perform the optimizations. So following are some of the blind validations results. This is a feed-forward neural network. So these are the results for blind validations of one scenario we shown here. So as you can see, they match quite very well, I would say, for this case, and also for the long short-term memory cases. So the reason is the model that we use are considered quite ideal, and of course, we are also examining some of the more complicated models in our work. But for the presentation here, we're just showing the ideal case. And these are the results and insight for feed-forward neural network after the optimizations. As you can see, the scenario 2 is what we call the simulation proxy. So what do we mean by simulation proxy is that we get the solutions from the proxy models, and then we feed back into the simulations and to produce the results. So in this case, we can see that, the two cases match reasonably well, and the percentage error between these two NPVs are about 3%. And we also do the simulations just by using the simulators itself. And when we compare to the proxy, it's even lower in this case. And the optimization time that we use is 6 times less by using the proxy itself. And the same goes to the LSTM cases. And in this case, LSTM shows better results and better accuracy, but the time used is large. So we have also performed some further works. In this case, we consider the proxy modelings and optimization under geological uncertainties. In this case, we actually expand the database itself by considering 10 realizations. And in this case, we did modifications in which we consider adaptive samplings. What do I mean by adaptive sampling in this case is that we actually iteratively expand the data while training and also optimizing in the whole workflow. So in this case, we will use some accuracy check of the output that we use. If this accuracy check is lower than certain preset values, then the data itself will be added into the database. So in this case, we actually take additional 66 simulations to achieve these results. And in this case, since we are considering 10 more realizations, what we call is the expected NPV in this case. And we also did the case for the simulations, and these are the results. And in this case, the values of proxy modeling is further highlighted because when we consider more realizations, it takes 7 days for us to complete. But when we use proxy, it takes 16 hours in our case. But of course, just now Candace had mentioned that there's a lack of big data is one of the challenges. But in this case, sometimes when you have too much data, there's also a problem because there's a curse of dimensionality in which when your database is too big, and it might take a long time for the training to be done. So in this case, we are also looking into some dimensionality reductions methods in a way that this database can be reduced in a way that the information still can be preserved. So some of the concluding remarks here is that we have illustrates how machine learning can be used to build a proxy model to solve reservoir management issues. And we have shown that it can reduce the computational footprints and also achieve desired level of accuracies. Like what I say, integrating more improvement is needed. Part of it is to reduce the dimensions, and also we have to also make it more robust and automated in a way that we can include some feature selections method in which we can select what kind of input can be useful to build a good proxy. In this case, we just select the input based on our understandings of the reservoir in terms of reservoir engineering. And of course, we also hope to mature this methodology in a way that we can use it in the other aspect of reservoir management, in which nowadays CCS and hydrogen storage has been part of the trend of the research, and this is also where our methodology can be applicable. So thank you very much for your attention, and thank you.